All right, everyone. We are in for learning activity 16 this week, which is our first lab. And what we're going to do is we're going to actually code up PCA, and we'll do this by hand. It shouldn't take us too long, but I want to follow along. I'll type it out. And we're going to be using a scikit example of the iris data set, which is pretty typical. But that's a pretty easy data set to work with. So it's an existing data set, and then we'll work with that, and then we'll code this up, and just kind of we'll use the AI too, because this is pretty common. So as the AI will probably find parts of this as we move along. So we're going to import matplot live .pyplot as PLT. We don't need, I'm not sure if we need these. And so I don't know if we need, we almost always need numpy, but we'll just pull these in as we come along. But we'll import MPL toolkits, toolkits. Toolkits.mplot3d, mplot3d. We don't need this. I think, no, we just need this. There we go. And then we do need numpy. So import numpy as np, and then we're going to do from sklearn import data sets, and we're going to do a decomposition too. And that is the data set we're going to pull in right there. And a decomposition is so cool now because, again, I've said this before, but man, this is so much easier to do now. Yeah, so, and to the point where it already knows what I'm going to type in next, so which is this np random seed, and then we're going to do the iris data set. If we give it a second here, it'll probably pull up the iris data set, or we'll just, no, I guess not, iris equal to, and then dataset.load iris. That's correct, X and Y. So we want a data. We want the iris. This is the main data. We also want the target, and then we're going to do a figure, plot figure 4.3. That's correct, and then all that is, that all looks pretty good. I think we're going to put in 11 projection 3D, elevate equal to 48. Yep, that's right. Azimuth 134. Yeah, that's, I think that we're good there. 134, and then I'm gonna set the axis, dot set position. Yep, that all looks fine. And then we're gonna do a plot dot CLA. And then we'll do a PCA decomposition and components. We are going to do it in 3 here. So this will be, I mentioned in lecture 2. This will be cool because we're going to actually do it in 3 dimensions, or 3 components. So we go through a fit process, and then we go through a transform here. We're going to close that off. And then we're going to create a for loop to run through the plot mechanism. So in other words, to create the visualization, we need to, we've got to create the plot. We got to go through matplot, and then this will give us an ability to actually take the data and then visualize it. So we got to create a for loop for this. So do a for name label, and there's 3 of them: the Setosa, Versicolor, and Virginica. And then and that all looks good. 0, 1, 2. So this is the index 0, 1, 2. Yep. And then for name and label in that data set, ax.text3d, and there's the means, and I'm just double checking here. X X. There should be 3. That's correct. Name, correct. Horizontal alignment equals center, correct. Okay, so that's good. And then we'll do a B box, dictionary, alpha 5, edge color W, face color W. It's all straightforward. I guess we'll find out if we get in trouble with that. All right. So we'll circle back on this. And then we're going to do a Y equal to np.choose. Yeah, that's all. This is just too crazy. With edge color K. Yep. And a scatter. That all. It's just great. It's amazing. AX dot X axis. Yep. Dot set tick labels. Yep, that's right. Y and Z, because we want 3. Yep, and plot show. I believe that's all. This is what's crazy, because now we've got an AI that helps us build this on the fly. It's so much easier now than having to code it in the past, which is you almost always code this stuff up, through just your experience and being able to be comfortable with this. Okay, be comfortable with Python. Okay, so we're gonna go ahead and run this. I'm not curious if this is gonna run on the first. Yeah, I didn't think it was gonna. I think we got a problem. Let's see, what is it saying? What is it complaining about? Edge color. Module NP has no attribute float. NP float was deprecated. Oh, okay. It has no float value. And Y equal to NP choose Y. And as type float. Yeah, I think that's what we need to do. As type float. Let's rerun this. Oh, hey, look at that. Perfect. It ran just fine. So that worked good. And it was quick. Okay, so that went through without issue. Just a minor data typing issue there. So there we go. And it created our little clusters and created it in a 3D plot, and worked just good. So now what this is doing is it's taking this iris data set here, and then creating the dimensionally reduced data, and then plotting that in 3 dimensions. But this doesn't tell me. I mean, this is great visually. This is great. But I want to actually. I'm going to create something here, and I'm going to use the AI to help me with this. So remember, I talked about the evaluation metrics. So let's just do this on the fly and see if we can't get this to work. Using the PCA iris data output, create evaluation metrics for explainable variance of our model. Okay. Let's see what it does here. Okay, so it's going to go through. Oh wait, here we go. There it is. Okay. Yep. Okay. So it took what we did up here and then gave me another one, and then gave me another line of code, well, a couple lines of code. This is what I'm looking for, this explain variance ratio, total variance, explain variance, total variance explain variance score. Yeah, okay, so let's run this and see what we get. Okay, yeah, perfect. All right, so this gives us something to work with. Wow, and it's really good. So when you look at this, it shows explain variance ratio being really nice. Wow, that's pretty nice, pretty amazing. So this equals to 100 right here. And so if we calculated that up at 0.05, that gets us up 0.053 to 0.92, then 0.017. If you add those up, we'll get right on 1 there, I believe. So and then your total explained variance of 99%, which is a really good score. That total variance explained. This means, in other words, what we're looking at, even though visually you're like, hey, I got some clusters, it looks like I've got some clustering going on. There's this data set has a lot, would have a lot of predictive power if I move this over into the supervised world. So these evaluation metrics tell me right up front, hey, this is something that is useful. Now, let's do one more. And remember the core plot. I want to see what, please create a core plot analysis of the iris data set. Okay. So we're going to use, oh yeah, Seaborn's good. All right. Let's see what this does. This is a new one, that you probably aren't familiar with and haven't seen, but Seaborn is a visualization tool. It gives us a lot more capability. It's going to run off and do a pip install, and then we'll see if it actually works here. It didn't. What is it complaining about? Create the core plot. Could not convert the string to float setosa. Yeah, it doesn't look right. Species. Explain the error. Okay. So, and then usually, all right. So we'll copy this. We'll copy that. And then we're going to bring that back over here. All right. And then we'll rerun it and see if it fixed that. And it did. How about that? That is what is amazing about this. So here is what we're doing here is it gives us, this is what I was talking about in terms of a core plot. So when I have a positive pedal, I'm looking at pedal length to sepal length. That means that that's a positive correlation here. It means that 0.87 means that as the sepal length grows, the pedal length grows. That also, the pedal width is also related to the pedal length. And then that's a proportional growth. But there's also some negative ones here, like sepal width is negative. In other words, it's inverse to pedal length. And then looks like negative as well for pedal width, sepal width, and pedal width. So this is a standard core plot, and we did a couple things here, and we're using an AI to help us out with this, which is fantastic because we can run through and spend more time looking at the code and understanding what we just built out here as well. But it also speeds us up in our data analysis. But yeah, to recap, we used an iris data set. We coded that out by hand. We got a visualization. Then to make sure that what we were looking at, we created an evaluation process to get the explainable variance, which shows pretty useful, which gives us predictive value. Typically, anything that's going to be over 0.6 or 60% is going to be okay. I'd like to see things above 70. Typically, between 70, 80, and 90 is a really good. Those are useful. When we fall under 60%, then the predictive power of what we're looking at isn't as good. The variance is not as good. Statistical correlations aren't as strong, so that not as useful. Doesn't mean it's not. I've used stuff right on kind of the middle there and been able to publish on that. Just depends on the data that you're looking at. And then we did a core plot just to kind of do another further analysis of everything. And So we're good to go from that perspective. So, all right. And it gives us a high-level perspective of everything going on as it relates to the total data set, and the data features cross-correlated with each other. So, okay, well, I hope you enjoyed that. That's all I've got for this lab, and be on the lookout for our Arduino lab. We'll head on over there and build something out, and then that'll just about cover it for this week. All right, thanks, and we'll talk to you later.